So you have a voting model where if you have a ternary branching Brownian motion, you can get Alencon. And you use a binary, you have a model with binary branching Brownian motion where you get Fischer KBP. And so now what you do is every time you branch, you kind of flip a coin and you either do binary or ternary and you take the voting rule associated to each one. And depending on the probability you pick, you get a different choice of chi. Okay? From a more biological point of view, you can think of this as putting in an Atelier effect. Atelier effect is the idea that your the reproduction rate of a species can increase as the population of the species increases, at least to some degree. So this is like cooperative defense or finding mates or due to things like this. Okay, but I'm not a biologist. I'm not going to pretend to be a biologist, but there's some motivation maybe to think about this choice. Okay, so let's just make some observations. So the first thing is that if chi is 0, this is just Fischer KPP. Okay, this is a pulled front, and its minimal speed is going to be 2. On the other hand, it's maybe not so obvious, but if you do a computation, you see actually that if you're between 0 and 1, you're not Fischer KPP exactly, but you're this Fischer KPP type. So your minimal speed is 2. And the Fischer KPP type is the ones where you stay below the tangent line. So this is a graph of f. This is graph of f. Okay. Now, even less obvious, but what people have sort of figured out is that if you are between 1 and 2, I'm going to put these in slightly separate categories. Let's say union, the set containing 2. This is no longer a Fischer KPP type. But anyways, the minimal speed is 2. So in particular, in this case, you have the tangent line, and there's some amount of time where you go above the tangent line. But the amount that you go above doesn't affect you because it's kind of small. And then finally, when chi is bigger than 2, this is no longer a pulled front, it's a pushed front, and your speed, C star, is going to be 2 over chi plus chi over 2. And let me just say that these are basically all pulled. This is pushed. And this is this pushmipullyu that Lenya discussed earlier. So unfortunately, the chi I'm using and the chi he's using are different. And I realized that this morning, but I thought if I tried to put a 2 here to make them the same chi, then there was no chance I would give a reasonable lecture, right? Because the chi would keep changing back and forth, and then no one would have any idea what's going on, including myself. So we'll just stick with this. Okay, so where can you find all of these computations? This is not anything that we did. This is Hadler and Rota, which is 75, and I want to apologize to the German speakers in the room for my total ignorance of the German language, because I believe he's German. Lenya, do you know? You don't know?
It's also 81, right?
81? There's 2 papers? Okay. Oh, yeah. Never let your collaborators come to your talks, okay? They just heckle you. Yeah, so I guess I should say that, by the way, this is all joint with Lenya and Jing. So on and Ryzhik. Okay. So that's great. We know the speed and we know all the sort of different things that happen here. But what can you say about convergence of the traveling wave, besides the fact that you do converge? Okay. So so here, let's look at our different chi regimes. Let's ask for a rate, and let's talk about how you do it. So I'm going to make a little table here. Okay, so let's start with Fischer KPP type. So is there a rate? It turns out that there is a rate. It's 1 over t. Okay. And this was done, the actual rate was done by Kolmogorov, who I think showed up It's nice to meet you, Cole. I've never met you before. I think 2019, I think. But this is building off of work of Amel, Nolan, Rokshov, and Ryzhik. And they had a series of 3 papers, which is, I think, 13, 17, and 19. Okay, so there's sort of 4 papers involved in getting this O of 1 over T. And okay, you saw the strategy already, right? Lenya talked about it. So it's maybe best, I think we've all suffered enough if I don't go into too many details. I mean that in the most loving way possible. But okay, it's, you do this self-similar variable stuff. You identify the constant, at 2t plus t to the gamma, and then you kind of pull back with a traveling wave, etc. And a kind of key thing here is that you need to know where the front is to an extremely high order of precision. Yeah?
Please emphasize what you mean by convergence rate.
So what I mean is, let's look at U star in L infinity to be less than or equal to whatever I put there. And what I mean is, like, choose the best shift. Okay, it's choose the shift that makes little u close enough. Yeah. Okay. So what you need to know is that you need to know, requires knowing that the front is at 2t minus 3/2 log t plus x infinity minus 3 root pi over root t plus 9/8 5 minus 6 log 2 log t over t plus O of 1 over t. Right? And why do you need all the way down to here? Well, if you want to get O of 1 over t close, you better be O of 1 over t close to where the front is. Right? You have to identify precisely where you are. Okay. All right. When chi is between 1 and 2, we have nothing. Okay, so there's nothing to say there. Okay, we can prove convergence, we can identify the constant, we can do this stuff, but we can't get any sort of rate, right? We just know that you do converge. Let's see if I've correctly judged my height. All right, good, I can do this. When chi is bigger than 2, so this is again, this is when we go to push, we actually get e to the minus gamma t. I don't want to stake my life on this, but I believe it's just some gamma, right? You don't really know what the gamma is. And in this case, you do something spectral. Okay, anytime you see like an exponential convergence rate, it usually means there's an eigenvalue in there somewhere. And so this is due to Sattinger 76. All right. So this is what we know. Okay. I'm trying to delay for a second so that people online can like stare at this for another second before I switch the boards. So what might you be unsatisfied? Why might you be unsatisfied with this? So why aren't we fully satisfied? Why are we unsatisfied with this? Well, the most obvious issue is it's incomplete. Okay, right? We're missing this whole middle section. All right. What else? Well, it's sort of complicated, right? I mean, especially the Fischer KPP thing. You know, you need to know this like this sort of expansion to extremely high order, and even though this thing is it's like it's incredible that we know it. And by the way, I should say that being able to crank out all these terms, I should mention that there's papers by Eric Brunet and Julien Beresticki and Bernard Derrida, where they have this like this like completely miraculous, beautiful method of just like pulling out more and more terms by having some relationship between sort of two integral things, and then you look at some singularity, and you just kind of, you know, there's a crank, and you turn it, and you just pop out term by term. So that's quite amazing. Okay, so back to what I was saying. If you want convergence rates, having to know 5 terms in the expansion seems a bit excessive, but also doing all this stuff with pulling back from the traveling wave. I mean, it's not, I don't want to, I'm struggling here to like not, I truly love it, but it is extremely complicated. Okay, I mean, you guys have seen the talk on it, so maybe I'll just leave it there and you can judge for yourselves. And then the other thing I want to say is it's kind of ad hoc, right? I have to switch. Yes, thank you. Sorry. All right, I appreciate it. It's kind of ad hoc, right? By which I mean, you have to do something different in every case, right? You do something fundamentally different in the pulled case and in the pushed case. And in the non-FKPP pulled case, you're kind of totally out of luck. So this means you're somehow maybe like missing something fundamental about the equation that's telling you converge at some rate. Okay, so that's what I want to say. That's what I want to start off by saying. And so that tells us that our goal for today is going to be kind of sort of one simple idea for all cases. So hopefully I'll give you the simple idea and you'll agree that it's simple and that it works for all cases. But again, I guess you can judge that for yourselves. All right, so that's the goal, and that's where the shape defect function comes in, right? So Lenya introduced this morning, but let me just say it again. Okay, we have a traveling wave. So this is the minimal speed traveling wave. And what we know is it's decreasing. Okay, and if it's decreasing, then what that tells you is that for any level set of your function, there's exactly one point that corresponds to that level set, that when you evaluate the function at that point, you get that level set, that height. Which means that for every level set, there is exactly one value of the derivative of u. So this tells me that there exists eta so that U star satisfies this first order ODE. So even though the traveling wave is defined by a second order ODE, by a miracle, it also satisfies a first order ODE. Okay. Really, this is just a property of being a monotonic function. Any smooth monotonic function satisfies the first order ODE for some sort of crazy reason, but it does. So we have this thing here. This quantifies how steep. So what Lenya talked about is this kind of quantify. This kind of tells you how steep u is, and that's kind of the reason why we started looking at it. So now what we call the shape defect function is going to be this function w coming from the solution to our PDE, which is minus ux minus eta of u. Okay. So w, so there's some things we can notice about w right away. Is this the one that like, yeah, okay. So what can we observe about this? So the first, which Lenya mentioned this morning, which is that w being 0 tells you that u is equal to a shift of the traveling wave, right? There's always a shift. Every time I write down u star, imagine I'm taking a good shift of it, okay? So somehow w tells you if you are the traveling wave or not. Something else that's less relevant to this talk, but which was important to why we started thinking about it, is w being positive is exactly telling you if u is steeper than u star. But now the thing that I really care about in this talk is the following, which is going to be a little bit vague for a second, which is that if I can tell you that w is small, say order epsilon, that actually this tells you that u minus some shift of the traveling wave is order epsilon. Okay, let me give you a caveat quickly, which is that this order epsilon is secretly order epsilon at the worst, but decays reasonably fast at plus or minus infinity. Okay, and why should this be true? Well, think of W as being an error term that says U satisfies the same ODE as the traveling wave up to this error term little w, right? Now, if two things satisfy the same ODE, they're the same, right? Just by uniqueness. But also, if you have a nice ODE, if two things start really close, then they'll stay really close. Okay? So that's basically what's happening here. I'm saying if I match up my traveling wave and my function at say the 1/2 level set, and they satisfy almost the same ODE, then they'll always stay really close. And this is going to be kind of the key fact that I'm going to use over and over again in the talk. All right.
Presumably, you're also using some sort of decrease key.
You mean for this L infinity? Yeah. No. Well, I mean, like, what does it mean to use it? I mean, I know that the traveling wave is exponentially decaying, so that kind of shows up. But the estimate that you get is going to be uniform, and actually it's going to get better the closer you get to infinity. Yeah. So I think it should be like epsilon times e to the minus some exponential in x as you go to infinity. Yeah.
And your order of epsilon on the right, is that not going to depend on time? Like,
so I'm saying fix a particular time, and let's say I tell you at that one particular time that I know this, with a caveat that secretly this is decaying as x goes to plus or minus infinity. It's epsilon times something that goes to infinity. Then I get this.
but that bound on the right is for all the, like, there's an order of epsilon that's independent of time, like for
So
later
if
time.
this is true at one time, then this is true at one time. So maybe you want me to put L infinity of x? Is that
Well, just that I'm wondering whether that order of epsilon on the right depends on the time that you're looking at then.
No.
Okay.
Pretend that I fix time and time shows up. It neither shows up in the constant here or the constant here.
Okay,
Yeah,
great. Yeah.
Okay. By the way, when I start writing here, I think I'm gonna this desk is going to be in the way, so I'll try to pick it up. But if you can't see at some point, just let me know. Okay, so that's my idea. That's what we're going to go for, and let's see where we can go from there. So okay, so I'm an analyst, as we established by writing down the PDE without the 1/2. So what do I want to do, right? What I want to do is I want to write down a PDE for the shape defect function. Okay, so Lenya very carefully did not do this for me, which I was very disappointed about because I didn't want to have to do it. So I think I will also not do it, but I will tell you what it is. So there's some long computation you can do that basically just uses this relationship that he gave us earlier today, which is that every single time you have a decreasing traveling wave, you always have this relationship. I guess this should have an of you. Okay, so just using this relationship, you can go and compute to your heart's content. And what you get is this is going to be equal to W times the U derivative of eta times C minus the U derivative of eta plus eta second derivative plus eta second derivative W. Okay, so we get this PDE. And of course, now we're like completely miserable, right? Because I don't know what eta is, but now I don't have to just know what eta is. I have to know what the derivatives of eta are. Okay, but it turns out that it's actually not so bad. So let's do this kind of in a case-by-case fashion. I want to start with sort of the easiest case, which is the pushed case, because it's a little bit more explicit. And so I can sort of show you some things a little bit cleaner. So this is the push case when chi is bigger than 2. Okay. So, well, what do we know? So here's me misjudging my height, I guess. U of x is like e to the minus lambda x. Here, lambda satisfies this relationship. And this is a relationship that's holding when chi is much bigger than when x is going to infinity. So this is telling you.
This is not visible. Should lower it a little bit, slightly.
Yeah. Okay. All right. This is also easier for me to write, so it's not so bad. Okay, so this tells me what u is doing, what u looks like when u is small. And if I use that along with this ODE, that tells me exactly what eta prime is going to look like near u equals 0. Okay. So now this tells me that eta u of 0 has to be like lambda. Okay. And now what this tells me is that WT minus WXX. Okay, what is this crazy thing on the right? Well, I'm going to do something a bit silly, and I'm just going to ignore a bunch of terms, but I'm going to promise you that those terms aren't a problem. And just tell you that really what we're going to care about is what all these terms look like when u is small. And when u is small, all that matters, the only term that's going to be non-negligible is this lambda term. So we get lambda, c minus lambda plus lower order terms that don't matter. Well, what is lambda times c minus lambda? Well, that's exactly this thing right here. So this is really w times 1 plus lower order terms. Okay. And what's so nice about this equation? This is essentially the linearized Fischer KPP equation. So we all know everything about it at this point. But just in case we don't, let's just notice that, okay, let's take W, so let me write it down here. WT minus WXX is essentially W, which tells me that W bar, which is e to the minus x minus 2t, is a super solution. And this tells me that W of t, x, well, let's say x plus c star t, because I care about what's happening at c star, is going to be less than or equal to W bar of t x plus c star t. And that is, well, I guess there should be a constant in here because you have to match up with the initial data. Some constant e to the minus c star minus 2t minus x. Okay. Let's just pretend we're only going to care about x being positive for a second, okay? Because you have to do something maybe a bit different for x negative, but let's just worry about x being positive for a second. In this case, then we get exactly, you know, that left-hand side of my relationship over there. That W is small, and so that tells me, so let's say at t, we get this, so then u of t minus u star, you know, infinity, up to shifting this thing, should be less than or equal to O of minus c star minus 2t. Yeah.
Sorry, I'm just a little bit confused by the fact that so you started, so we're in the pushed case, so there is a lambda which corresponds to the speed, and you arrive at an equation where there is no lambda.
Isn't it amazing?
Slightly
it's
worrying.
kind of the magic though, right? It's the relationship you always get always gives you a 1. It's going to happen in the push case and the pulled case and the push-me-pull-you case.
Okay.
And it's why the whole thing works. So to give away the ending, the front for W, the front for the W equation always sits behind the front for the U equation. And that's what gives you the decay of W. Because if I write down this equation this equation, this thing is positive. So this whole thing is going to be positive for at least some choices of u. So there's going to be some region where W has positive growth. But the point is that region moves too fast. It just flies off to the right. And so W gets kind of trapped in the region where everything's decaying. Does that answer your question?
Yep.
Okay. I think someone was laughing online. Hopefully not at me. Okay. All right. So why does this work? Or what happened here? What's the principle that we want to live by? This is hopefully my simple idea, is that the U equation has front at C star T. The W equation has front 2T. And so therefore, W will be less than or equal to, well, as Lenya told us this morning, you always want to remove an exponential, which tells you that shifts in W by some amount change W by e to the minus that shift. So if you have this difference between your like fronts, you have a shift of that amount. And so you end up with something like, let's say, the difference between these. Okay. Now, I'm being very vague when I said W has front at 2T, because it kind of makes no sense, right? The maximum of W should be where the front of U is. But what I'm saying is kind of, if you look at the equation for W, you see Fischer KVP, and Fischer KVP up to lower order terms is what we see. And Fischer KVP has front at 2T. So I mean, like the equation is a kind of a natural front. And if you forget that W and U are related, then that's the sort of principle you use. Yeah.
You didn't tell us also what to do with x negative, right?
I didn't tell you what to do with x negative. Okay, yeah, it's so this is part of the talk where I'm sort of lying to you, because this is like there are these stories of like so when Apple came out with the iPhone, right? Like Steve Jobs had this big thing, he like showed everyone how to use it, right? And then like 10 years later, people were like, actually, there was no iPhone at that time. There was like someone behind the curtain, like manually changing the screen every time he pretended to push a button. Because they like hadn't created it yet, but it was like, you know, they knew that they would be able to create it, or they were confident. I think this talk is kind of a bit like this. Like some of these things I have much more, some of these things I like know are true, and some of these things I like haven't quite worked out to the full extent. Okay. So I don't want to tell you exactly what's going on. So behind the front, I haven't really thought about it too much for the pushed case. Okay. I can tell you exactly, I'll be, you know, if you ask questions, I'll be perfectly honest on what we know, what we don't know. But so it could be that this is not exactly the correct exponent. Yeah. But it might change depending on what the exponential decay looks like behind the front. Okay. So I suspect if you get something else here, it's going to involve something about f prime of 1. Okay, that's for computations for another day. I think every talk, like if you give a proof, you have to lie, right? And so, okay, maybe my lie is bigger than other lies, but hopefully it's not too big. Okay, so case chi equals 2. So this is the push-me-pullyu case. So in this case, I mean, think of the computations I did for the push case, for the traveling wave and what it tells you about eta. Well, it's the exact same thing, right? Those computations won't change at all. So similarly, we're going to get something like WT is like WXX plus W. Okay. Now, what do we know? Well, W is a bounded function which approximately satisfies linear Fischer KVP. And the big moral of this first Amel, Nolan, Ryzhik, Rokhov, I feel like I have to write Amel so people don't think I'm claiming that I was a part of the paper, because I wasn't. But I'm not an N or an R or an R. So the first Amel, Nolan, Ryzhik, Rokhov paper, kind of a big principle of it was that if you satisfy linear Fischer KVP and you're bounded, then your kind of front has to be like 2t minus 3/2 log t. Okay, so on the other hand, as Lenya detailed this morning, the front for you is 2t minus 1/2 log t. So this tells us, based on our principle of w being smaller than exponential minus the difference, is that w has to be less than or equal to O of exponential minus, well, we have 2t minus 3/2 log t, we have 2t minus 1/2 log t, so the difference between those is log t, and so we get O of 1 over t. Okay. Do you have a question? I have to get another piece of chalk, so you have time there. Okay. So now let's do one last case, which is chi less than 2. This is the sort of Fischer KVP, the semi-Fischer KVP case and the Fischer KVP case. Okay. And now in this case, what do we know? Well, we know that u star of x is like x e to the minus x when x is big. So what this tells us is that eta of u is terrible. It looks like u times 1 plus 1 over log of u plus dot 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 plus lower order terms. Okay. And now it's kind of a big computation, but if you do that big computation, what you get is that wt minus wxx is going to be w times 1 minus 2 over log of u squared plus lower order terms. Okay. And now you look at this and you think, what kind of weirdo would be psychotic enough to look at an equation like this, right? And the answer is there are 2 of these such people. So in fact, myself and Émeric Bouin looked at an equation like this a few years ago, and it turns out that this equation is associated to a front at 2t minus 5/2 log t. Now we had no idea that it would come to be useful here. Actually, when Jing and I were doing computations and we found this thing, it was like a miracle occurred. I felt like you know, we were given something divinely like coming down from the heavens, because I was like, I think that 2 people have read this paper in the world, and those 2 people are me and Émeric. Okay, and probably some poor referee was forced to read it as well. But other than that, this is actually u. So you might say, okay, did we really look at this equation? And the answer is no. We looked at an equation where this function was the same as this function. But in fact, the same strategy applies like basically out of the box. Because essentially what you do is you look at kind of long scales and you just substitute in what the traveling wave should look like, and you can do that same thing here. The reason that we were looking at this is because this is related to something we were seeing when we were doing a project with Lenya on the non-local Fischer KVP, which of course Sarah had a wonderful paper on, and then Sarah and Julian and some other people, and now I'm getting. Was Eric a part of this? And then I think there are 4 authors, right? Or was it? There was the decay of mass and blah, blah, blah. No, with Luigi. Oh, that's really bad because he, is he here?
Yeah.
He's online. Okay, well then he can't yell at me. But Luigi, I'm sorry, I forgot you. No, I knew that. I should have known that. Yeah. Okay. Okay, so we have this front at 5/2 log t. And of course, u has a front because it's semi-FKPP has front at 2t minus 3/2 log t. And so this tells me that W. Oh, I forgot to write the closest to the traveling wave up there to drive home the point. I totally forgot. I'm sorry. I'll do it this time though. O of exponential of the difference between them. But of course, what's the difference? It's exactly log t again. And so that log t that we saw at the beginning that Cole got, well, here's hopefully maybe an explanation for it. And by the way, something that I don't think we can do, but that Cole points out in his paper, what he sees in his paper, is that the O of 1 over t is sharp. You can't get any better than it. So this tells me that, okay, u of t dot minus u star L infinity is less than or equal to O of 1 over t. And I should write that same thing here. Okay, but I can't reach, so we'll just put a squiggle. So that's what the squiggle means. So I'm going to finish in like 2 seconds. So do you want to, that way then you can ask me a question. So then if no one else asks me a question, then you'll have saved Jason from asking me a pity question. So my point is, for all of these cases, it just boiled down to writing out an equation for u, finding its front, not to high order, just the first two terms. In some case, just the first term. Writing out an equation for w, finding its front, and then just finding the difference between the two. And that gives you the convergence, right? Okay, and then here's where I'll stop. Thank you very much for your attention. Sorry.
I don't want to hog the mic here, but so it's very, thank you for the very nice talk. I mean, so if I understand correctly, what happens is that W and U have front position which are not the same, right? So
Exactly,
they differ.
yeah.
And that difference is what controls the rate of convergence of U to U star.
Yeah.
But so can you give me, I don't see the intuition why W should have a different front position. Why is it behind the front of U? I mean,
Yeah, I mean, the problem is that I think I have trouble answering that because it seems kind of a miracle that W satisfies an equation at all. I mean, this was like, you know, you do PDE, you have a quantity you care about, you desperately hope that it solves a PDE, so you just start computing. So I don't know. I mean, once you see this term, this is always going to give you lambda times c minus lambda. So you know this is always going to have kind of a 1 as its dominant term. And everything after that is going to be corrections involving u. So no matter what c is, right? You choose f to be some crazy, you know, choose chi to be anything you want in the world, but you're always going to get a 1 here. Okay. So that tells you automatically that if you're in the push case, you're going to see a different speed. Now, why in the semi-FKPP case you have this miraculous minus 2 over log u squared? I mean, that's kind of I don't know. We just computed it and it came out, and like I said, it's like something coming from the heavens. You're happy that it shows up. The thing is that it's very sensitive because if that log of u squared is something else, if that power is bigger, then you get a 3 halves log t. If that power is smaller, then you get an algebraic delay. If that 2 is something different, you don't get 5 halves log t, you get something else. So if you didn't get that 2, it's like if you had like 3 up there, then you would get something bigger, if you smaller. A bigger delay difference, so a smaller, better rate of convergence. For the non-local Fischer KVP thing, analog, by the way, that 2 is like the critical case. That has to do with like the decay of the kernel, and that 2 is like the kernel decaying like 1 over r cubed. So 2 is, you know, the exponent of r minus 1.
Any other questions?
I wish to connect it to Raphael's talk. So in Raphael's talk, so he said, looked at the bistable equations. So he had this nice picture with the stable manifold where you converge to when you're outside of the stable manifold, and then you're at the traveling wave, right? And you converge exponentially fast to it, right? And so this with the shape defect function, you should, I mean, it's kind of describes how fast you convert to the stable manifold, right? So it kind of allows to well to separate the coordinates in this in this setting, right? Okay, it's maybe just my naivety, but maybe is there something deeper to it or not?
I don't know.
So does this shape defect function then give something new in this respect, makes things more explicit, or?
So I will say that I have not thought at all about the bistable case. I haven't thought at all about what changes if f becomes negative. So I can't guarantee that I'm.
But I guess the same picture should then actually hold in your case as well, right? I mean.
Yeah.
So,
but now I'm worried that I'm not remembering Raphael's talk very well. Raphael, did you have rates of convergence?
Using the exponential convergence. We're actually using the variational proofs that Lenya mentioned this morning.
Yeah. So in the pulled case, there's like various different proofs of the exponential convergence. So I mentioned the Sadinger paper, but then of course the ones that Lenya mentioned as well also give other ways of getting the exponential convergence. So the thing that I like about this is that it's like hopefully I've told you that it's kind of like one idea that you can kind of use in all cases. Otherwise, if you want to use this like energy formulation to get convergence rates, that's great, but it really, no one's done anything for pulled. The moment you get to pulled, the energy doesn't make sense. Okay, maybe we can do something with the shape defect function as Lenya wrote down this morning, but beyond that, yeah, I think, it's like there are a flurry of papers in the 2000s and then kind of.
Okay, are there questions online or?
No, there are no questions online unless people raise hands now. Oh, yeah. So Bernard Derrida has a question. Bernard, you can unmute yourself. And
yes. Okay. So I have a simple question for FKPP. When in the long time limit, when you multiply by exponential x, you get this scaling function z exponential minus z squared. Is it clear? Lenya talked about that. You see, when you rescale space, you have a kind of universal shape. So
yeah,
you take the wave, you multiply by exponential x. Here, do you have similar results, or so you just take the tail and you multiply it by exponential x? What do you see?
So in all of this, I'm sort of not touching u at all, right? The only things I use about u are to deduce things about. So in all of this, I'm saying, suppose I sort of know where the front of u is already, and then everything else is kind of how do you use that knowledge to get convergence rates? So I think the thing that you're asking about is so in Lenya, in the proofs that Lenya talked about, it's really important to understand what the shape of the traveling wave is, so you can kind of make some transformations to little u, so that you can get a PDE for which you can kind of prove convergence. Here I'm kind of not doing any of that stuff at all. I'm saying, suppose someone else has done the hard work to figure out where the front is, not a crazy high order, but just to say the first two, at most the first two terms. And then how do you use that information to get convergence? Does that make sense?
Okay, thank you.
Does that answer your question? Okay, thanks for the question.
Okay, let's thank the speaker again.